In the following video, I will answer for you the January 2011 Decision 1 OCR paper, question 6. This question was about the simplex method. Okay, let's start straight away by having a look at the question. It said, consider the following linear programming problem, which was a following minimization with the certain constraints. Effectively, it then shows that this problem is equivalent to this problem and asks you to show how to get from this problem to the equivalent maximization problem. Just taking a look at the problem first of all, it's a minimization problem, okay, and we know that a standard linear programming problem for the simplex method is a maximization, so we know we're going to have to change that to a maximize somehow. Also, one of the constraints is a bigger than or equal to constraint. But we know that to use the simplex method, we want all the constraints to be less than or equal to, so we're going to have to modify that. And lastly, we need a non-zero constraint for the variables, but here it just tells us that a, b and c are less than 6, 8 and 10 respectively. It doesn't tell us that they're bigger than or equal to 0, so we want a bigger than or equal to 0 final constraint. So part 1 of this question is effectively about transforming a non-standard linear programming problem to a standard one so we can use our normal simplex method. Okay, the way it says to do that, it says that because a is less than or equal to 6, if we were to subtract a from both sides, you would get 0 is less than or equal to 6 minus a. Now you've got something bigger than or equal to 0, and you can call that a new variable. Call that a new variable, say x, and let x be defined as 6 minus a. And in particular then, what would a be in terms of a? A would be 6 minus x. Okay, so you get all of that from using the inequality a is less than or equal to 6 and setting a new variable. We can do that with b and c as well. Because we know b is less than or equal to 8, we can subtract b off both sides and say 0 is less than or equal to 8 minus b. Define a new variable y to be 8 minus b. And then b in terms of y, well, b would be 8 minus y. Okay, and lastly, c is less than or equal to 10, right? So subtracting c off both sides, 0 is less than or equal to 10 minus c. Let z, a new variable, be 10 minus c. And then c in terms of z would be 10 minus z. Okay? And now you've done this part of the constraints. You can say that a less than or equal to 6, b less than or equal to 8, and c less than or equal to 10 is the same as, or is equivalent to, is the same as x bigger than or equal to 0, y bigger than or equal to 0, z bigger than or equal to 0. So you've done this first part of converting that constraint into that constraint. Okay, now we're going to try and change the objective function by substituting in for a, b and c in terms of x, y and z, and we're going to do the same for the constraints to modify these 4 lines into these 4 lines. Okay, so I'm going to do that on the next page. Now, we knew, just to remind us, that we defined x to be equal to 6 minus a, y to be equal to 8 minus b, and z to be equal to 10 minus c, so that a was 6 minus x, b was 8 minus y, and c was 10 minus z. Okay, now if we simply substitute for a, b and c into these lines here, we can modify them to look like how question part 1 asked us to. So it's a simple substitution. So let's call that line 1. I'm going to say line 1 equivalent to, minimizing this would be equivalent to maximizing the negative of that. So it would be equivalent to maximizing minus 2a plus 4b minus 5c plus 30. Okay, so that's a fair line to write. And now we're going to substitute in. So subbing A, B, and C, we get, okay, the algebra might get a little bit messy here, so let's just keep it all tidy. Minus 2, A is 6 minus X, plus 4, B is 8 minus Y, C is 10 minus Z, so minus 5, 10 minus Z, plus 30. Okay, now we expand it all out. We would get minus 12 plus 2x plus 32 minus 4y minus 50 plus 5z plus 30. Okay, just taking the x, y, and z first of all, I'd get 2x minus 4y plus 5z. Okay, minus 12 plus 32 is plus 20. Then minus 50, you get minus 30. Then plus the 30 would bring you to 0. So we have 1 is equivalent to maximize this objective function here. And let's just check we've got that right. 2x minus 4y plus 5z, 2x minus 4y plus 5z, we've got it. So we've done the first part. And I'm afraid we just have to go through by showing line 2, line 3 and line 4 turn out to be equivalent to what they ask us to in the question. So I'll change pens just to show the difference. So 2 is equivalent to just before I want this to be a less than or equal to inequality, so I want my variables to be on this side of the inequality here. So this is equivalent to, the same expression would be equivalent to minus 3a minus 2b plus c is less than or equal to minus 10. Okay, so I'm multiplying both sides by minus 1. So 2 is equivalent to this, and now substituting in sub a, b and c, we would get minus 3, a is 6 minus x, minus 2, and b is 8 minus y, and c is 10 minus z, is less than or equal to minus 10. Okay, we'll tidy it up. We get minus 18 plus 3x, minus 16 plus 2y, plus 10 minus z is less than or equal to minus 10. Okay, now we'd have 3x, just taking the x, y, and z, plus 2y minus z, and then minus 18, okay, minus 18 minus 16, and then plus 10 would give me minus 24, and I would add 24 to both sides to keep all the numbers on this side, so I should get over here 14. So let's check that looks like what we were trying to get. 3x plus 2y minus z is less than or equal to 14. 3x plus 2y minus z is less than or equal to 14. We have done the second part there. Okay, let's continue. Let's have a go at line 3 now. This was line 3. Line 3 and 4 should be slightly easier. 3 equivalent to minus 2. A was 6 minus x plus 4. C was 10 minus z less than or equal to 35. And this should be quite easy to tidy up. Minus 12 plus 2x plus 40 minus 4z less than or equal to 35. And tidying that up, you get 2x minus 4z less than or equal to, or on this side, 40 minus 12 will give you 28, and subtract 28 from both sides, so you should get less than or equal to 7 when you tidy that up. So just checking back, 2x minus 4z is less than or equal to 7, 2x minus 4z is less than or equal to 7, you've done that. And lastly, 4 is equivalent to 4a, a is 6 minus x, and minus b, which was 8 minus y, less than or equal to 20. Just tidying that up. 24 minus 4x minus 8 plus 8y less than or equal to 20. Minus 4x plus 8y. And then you get 24 minus 8, 16. And subtract 16 off both sides, you would get less than or equal to 4. You could divide everything by 2, just checking back at the exact answer. They don't want you to divide it. Oh, sorry, going back here, sorry. When I expanded this out, this should be minus 8 plus y, my apologies. And that would have been your final inequality that you want to show. Okay, so now we've shown that all 4 lines of this are equivalent to a standard linear programming problem. Okay, that was for 3 marks. That was quite a lot of algebra, but fairly easy, but a lot. So you should have just been running through that fairly quickly, just you know, keeping things neat and tidy as you show your workings. Next, it says, well, now consider your standard linear programming problem and put it into a simplex table, and then perform 2 algorithms or 2 stages of the simplex method, and at the end tell us what A, B and C were after those 2 stages. So now we're in familiar territory. We've got a maximization problem, all 3 constraints are less than or equal to, and we've got a non-negativity constraint for our variables x, y and z. So everything is as we like it. I'm going to define Q to be equal to 2x minus 4y plus 5z, the thing we're trying to maximize, and as I always do at the start of the simplex, I'm going to make my objective function equal to 0. Okay, and this is the basis of what I'm going to do with my simplex tableau. I'm going to introduce a slack variable s here to make that an equals, a t here to make that an equals, and a u here to make that an equals. So I'm going straight from here to the simplex tableau. We care about q, we care about x, we care about y, we care about z, and we care about a slack variables we're going to introduce s, t, and u, and we care about the values of each of these functions, so the values. Okay? So set up our table as such, and the initial tableau is going to have the coefficients of this line here. Well, we've got 1q minus 2x's, 4y's minus 5z's, no s's, no t's, no u's, and the value of this function is equal to 0. And introducing my s, t, and u here, we're going to get 3 equations. I'm going to get no q's in either of those, so I'm just going to put 0, 0, 0. I'm going to get 3x, 2x minus 4x, so 3x, 2x minus 4x. 2y, no y, and 1y, so 2y, no y, and 1y. Minus 1z, minus 4z, and no z. Here we would have had 1s, no t, no u. Here we're going to have 1t, so no s, 1t, no u. And here we're going to have 1u, so no s, no t, and 1u. The values are 14, 7, and 4. 14, 7, and 4. So by putting that in the initial tableau, we've got some marks there. So we've put our problem into an initial tableau there. Okay. At this stage, what I said to you, I'm going to perform the first stage of the algorithm on this page here. Right, I'm just going to underline that first tableau there. Now, what I said we do is we look across the top row and we see the most negative, which is here. Then we perform the calculation of the value divided by each entry in that column. Now, we ignore negatives or zeros in this column because we ignore 14 divided by minus 1. We don't take into account if it's a minus. We ignore that minus. And 4 divided by 0 is infinite. So we can't do any pivoting on that column currently. So I'm going to ignore that. And I'm going to go straight to the other negative, which is this one. I look down this column here, and I do the value divided by that column, the value divided by that column, and I don't do that divided by that because that's a negative. So I only perform two calculations. I say to myself 14 divided by 3, and I say 7 divided by 2. And I work out which one's the smallest out of those. Okay, the smallest divided by... the smallest of those two is going to be this, which is 3.5. Okay, so I'm going to pivot on that element, that entry of my simplex tableau. By that, I mean I want that number to be 1 and I want all these numbers to be 0. Okay, so I'm going to have to perform row operations with this row 3 to make all of these 0 and row 3 turn into a row where that number's 1. Okay, how do I do that? Well, I'm going to need a new row 1. I'm going to call that. I'm going to need a new row 2. I'm going to need a new row 3. And I'm going to need a new row 4. Row 3 is the easiest. My new row 3 is going to be my old row 3 times a half. A half times my old row 3. Simple. So I'm going to write that in to start with. This one, everything on here needs to be multiplied by half. I'm going to get 0, 1, 0, minus 2, 0, a half, 0, and 3.5. Okay, so that is my first row operation there, done nice and easily for us. Okay, to get the other ones, well, to get that to be a 0, all I need to do is take my row 1 that currently and add row 2. So my new row 1 is going to be my old row 1 plus row 2, right? So I'm just going to add that to that and write the answer. This plus this is 1. This plus this is 0. This plus this is 4. This plus this is minus 9. This plus this is 0. This plus this is 1. This plus this is 0. And 7 plus 0 is 7. Done that first one. Okay, how am I going to get this to be a 0? Well, I'm going to take my old row 2 here, well that's a 3, and I'm going to have to subtract 3 over 2 lots of my row 3. If I subtract 3 over 2 lots of 2, I'm going to make that a 0, and I'll do that with everything. So, what we've got is we've got that, take away 3 over 2 lots of that is 0. That, take away 3 over 2 lots of that is 0. 2, take away 3 over 2 lots of 0 is 2. Minus 1, take away 3 over 2 lots of minus 4, okay, would equal 5. Type that in your calculator. 1 minus 3 over 2 lots of that is 1. 0 minus 3 over 2 lots of that is minus 3 over 2. 0 minus 3 over 2 lots of 0 is 0. And 14 minus 3 over 2 lots of 7 would be 3.5. So again, you get 3.5 here. Okay, and for the last row 4, what would you do? Well, to get your new row 4, you take your old row 4 and you add 2 lots of row 3. So you take your old row 4 and you add 2 lots of row 3. So let's write that out. This plus 2 lots of this is 0. This plus 2 lots of this is 0. This plus 2 lots of this is 1. This plus 2 lots of this is minus 8. This plus 2 lots of this is 0. This plus 2 lots of this is 2. This plus 2 lots of this is still 1. And 4 plus 2 lots of 7 is 14. So 4 plus 14 is 18. And that is the result of your second part of the tableau. Okay, your second operation. So what I'm going to do is I'm going to take this and I'm going to move it onto another page. Okay, I'm going to move it up like this. Okay, so that's our second tableau. Now what we're going to do is we're going to perform the third, the second iteration in our simplex method and get the third tableau. So what we do is we look across the top row and find the negative. There's negative minus 9. We do that divided by that, and that divided by that, and that divided by that. However, we ignore that and that because they're negatives, okay? So we don't bother doing those calculations, and therefore this one is the only one left, so we must have to pivot on the 5. That means we're going to make that number a 1, that is 0, that is 0, and that is 0, okay? So, in order to do that, we're going to get a new row 1, we're going to get a new row 2, we're going to get a new row 3, and we're going to get a new row 4. Okay, let's do the row 2 first. Our new row 2 is going to be the old row 2 times a fifth. Okay, times a fifth. And what are we going to get? Well, let's just write it out. We're going to get 0, 0, 2 fifths, 1, 1 fifth, minus 3 tenths, 0, and 3.5 divided by 5 is 7 over 10. So we're going to get 7 over 10 here. Okay, now how are we going to get the others? It's going to be slightly complicated, but so you're going to have your calculator at hand here. Let's do row 1 to start with. We're going to take our old row 1 and we're going to add to it, okay, 9 fifths of row 2, of the old row 2. So we're going to add 9 fifths of this row. So let's type in what we get. 1 plus 9 fifths of that is 1. 0 plus 9 fifths of that is 0. 4 plus 9 fifths of 2. So 4 plus 9 fifths of 2, we're going to get 38 over 5. Leave it in fractions, it's easier. This plus 9 fifths of that is going to be 0. 1 plus 9 fifths of that is 9 fifths. This one's going to be 1 plus 9 fifths of minus 3 over 2. Typing that in your calculator, you get minus 17 over 10. So you get minus 17 over 10. And this plus 9 fifths of that is still 0. And 7 plus 9 fifths of 3.5. So 7 plus 9 fifths of 3.5. And you get 133 over 10. 133 over 10. Okay, so as you can see, you really need your calculator at hand here to work these out, to do it quickly for you. Okay, let's look at row 3. How do I get my new row 3? Well, I'm going to take my old row 3, okay, and I'm going to add to it 2 fifths of the old row 2. So I'm going to take this row and add 2 fifths of that row. 0 add 2 fifths of that is 0. 1 add 2 fifths of that is 1, sorry. 0 add 2 fifths of that is 4 fifths. Minus 2 add 2 fifths of that is 0. 0 add 2 fifths of that is 2 fifths. A half add 2 fifths of 3 over 2. So a half plus 2 fifths of minus 3 over 2, and you get minus a tenth. This plus 2 fifths of that is still 0, and 3 over 5 plus 2 fifths of 3 over 5, 3.5 plus 2 fifths of 3.5 is going to be 49 over 10. 49 over 10. Okay, and the last one here, we're going to take our old row, to get our new row 4, we're going to take our old row 4, okay, here, and we're going to add 8 fifths of that of row 2. We're going to add 8 fifths of the old row 2. Okay, let's try and do it. That add 8 fifths of that is 0. That add 8 fifths of that is 0. That add 8 fifths of 2. So 1 plus 16 fifths effectively is going to be 21 over 5. That's going to be. That add 8 fifths of that is 0. That add 8 fifths of that is 8 fifths. That add 8 fifths of that, so 2 plus 8 fifths of minus 3 over 2 you get minus 2/5. That add 8/5 of that is 1, and 18 add 8/5 of that, so 18 plus 8/5 of 3.5 is going to be 118 over 5. So at this stage now, we have actually performed our 2 iterations of the simplex method. And remember our columns of the simplex, we called this Q, this was X, Y, Z, S, T, U, and the value. Okay, so we've done what they've asked us to do. Let's just read off what this is telling us. Well, it's telling us currently that Q, the thing we were trying to maximize, is equal to 133 over 10. It's telling us that X is equal to 49 over 10. Y, well, it doesn't have a 1 and all zeros, so Y is equal to 0. Z is equal to 7 over 10. S and T are both 0. S and T are both equal to 0. And U is equal to 118 over 5. Okay, so I'm just going to convert these into decimals. This would be equal to 13.3, X is equal to 4.9, Y is equal to 0, Z is equal to 0.7, and U is equal to 118 divided by 5, which is 23.6. Okay? Okay, I'm going to take this, what we got from our simplex method, and I'm just going to translate that back into our original problem. Now remember, our original problem was that, okay? And what we ended up doing was maximizing the following. We ended up maximizing the following problem. The following problem there, okay? So we know, so basically, what is the minimum value of this? Well, if we know these two are equivalent, the maximum value of this thing here, the max of 2x minus 4y plus 5z is equal to 13.3, and we know that was equivalent to that by a substitution. We know that the min of 2a minus 4b plus 5c minus 30 must be equal to minus 13.3, the negative of that. Now we have to state at what values of a, b and c this is true. Well, we know that x, when we solved this, x was equal to 4.9, and we said that a was defined to be 6 minus x, was 6 minus 4.9, so a must equal 1.1. Okay, at this point we've said y is 0, and we know that b is 8 minus y, which is 8 minus 0, so b must be 8. Z was equal to, here we had 0.7, and we defined c to be 10 minus 0.7, which we're going to say obviously therefore is 9.3. So the minimum value of this is when x is 1.1, y is 8, and z is 9.3. At this point, let's just double check that all made sense. What is the value of 2a minus 4b plus 5c minus 30? Okay, well, 2 lots of a, 2 lots of 1.1 is 2.2. 4 lots of b, well, 4 lots of a is 32, so minus 32. Okay, 5 lots of c, well, c was 9.3, so 5 lots of c, 5 times 9.3 is 46.5, so you're going to add 46.5, and you're going to take away 30. Work that out, 2.2 minus 32 plus 46.5 minus 30, as we thought, was equal to minus 13.3, which was the minimum value which we've stated. And if we check if we check A, B and C satisfy these inequalities, they indeed do. And obviously, if A is 1.1, it's less than 6, less than or equal to 6. If B is 8, it's less than or equal to 8. And if C is 9.3, it's less than or equal to 10. Hence, we found our answer to this simplex method problem. I hope you found the following video useful in your revision. Thank you for listening.